Hello everybody, it's Kami Suleiman, and if you're new here, I'm a medical student and I make science videos related to the MCAT, AP exams, and just STEM fields in general, and I also make pre-med content. So today we're going to be talking about kinematics, which is a topic within physics that you're certainly going to encounter at some point in your career if you choose to pursue a career within STEM. So whether you're a pre-med preparing for the MCAT or an engineering student for your intro to physics class, or even a high school student preparing for your AP exam. And today we're specifically going to be focusing on projectile motion. We're going to be addressing one specific question, but I think the understanding that you'll derive from this video will guide you to answer any projectile motion question that comes across your way. And I will provide you with some comprehension questions at the end of this video, so try those out and let me know what your answers were in the comment section down below. The question we're going to address is that if I wanted to throw this ball as far out as I possibly can, what angle would best achieve that? Is it a 0-degree angle, a 30-degree angle, a 45-degree angle, a 60-degree angle, or a 90-degree angle? So let's run this little experiment real quick and then we'll start with the physics stuff. All right, so here's a 30-degree angle throw. Of course, I'm going to be approximating to the best of my ability. Let's go for our 45-degree angle. And finally, our 60-degree angle throw. So it seems like that was similar to our 30-degree angle throw, but less than our 45-degree angle throw. Before we get started, be sure to like and subscribe to stay up to date with all of my content. Projectile motion is a source of confusion for many students, and that's because it contains two motions within one question. So it's two-dimensional motion, and you need to treat each of these motions separately. So you have the X, or the horizontal component of the motion, and then the Y, or the vertical component. Now, in order to calculate the maximum distance, of course, we're going to be focusing on the X component. But as you'll see, we do still need to consider the Y component. So let's first choose one of our kinematics formulas that's going to allow us to calculate the maximum distance, or the range. And that's going to be the second formula right here. Change in X equals the initial velocity in the X component times time minus half at squared. Now, you can eliminate that second part of the equation because there is no acceleration acting in the X component. The acceleration is only acting in the Y component. So our equation simplifies to change in X, or the range, equals the initial velocity in the X component times time. But how are we going to figure out how long time is? That is, how are we going to figure out how long this ball will be in the air? Well, that depends on the Y component, because remember, what's pulling the ball towards the ground is gravity, and therefore the Y component of the velocity will determine how long this ball will be in the air. So now let's choose one of our kinematics equations to calculate the total time that the ball will spend in the air. So that is from the moment I throw it to the moment it hits the ground. When choosing a kinematics equation, you'll notice that each one is missing one variable. Of course, you want to choose the one that's not missing your variable of interest. So before we choose it, I did want to note one thing, and that is that when this ball is at its maximum height, it'll be at a velocity of 0. So we can use that to our advantage. That'll be our final velocity, basically. And that's because when the ball leaves my hand, as it starts to approach its maximum height, it'll be slowing down because the velocity vector is going up, whereas the acceleration vector, or gravity, is going down. And therefore, it's constantly slowing down, and then eventually to reach a point where it'll start to speed up down towards the ground again. Well, that transition point is where velocity will be equal to 0. So we can define this midpoint as our final velocity. That is the final velocity from when I throw the ball until the ball reaches halfway of the trip, and then just multiply that by 2, and there you have your total time. So let's choose one of our kinematics equations that'll allow us to calculate time, and that is this one. Final velocity in the Y component equals initial velocity in the Y component minus acceleration times time. Acceleration is, of course, gravity. All right, so plugging in 0 for final velocity, because we defined the final point as that midpoint right there. So that's going to be 0 equals initial velocity minus gravity times time. Now let's do our algebraic rearrangement. Time is going to equal the initial velocity over gravity. Now let's multiply this by 2, because recall how we said this is just the time until that midpoint. Well, it turns out that the ball is going to spend the same amount of time back down to the ground, under the assumption that it'll end up at the same height that it started and that there's no air resistance. So the equation ends up being total time equals 2 times the initial velocity over gravity. Now let's plug this into our initial formula, which recall was change in X, or the range, equals initial velocity in the x component times time. So let's plug in what we have for time there. So 2 times the initial velocity in the y component over gravity. So how do you break up the velocity vector into a y component and an x component? Well, we're going to use our basic trigonometry. So in order to calculate the velocity in the x component, you're simply going to multiply the initial velocity times cosine theta. And in order to calculate the velocity in the y component, you're going to say initial velocity times sine theta. So our equation ends up being range equals the initial velocity times cosine theta times the initial velocity times sine theta over gravity. Again, we're just cleaning it up right here. So you end up with velocity squared times cosine theta times 2 sine theta over gravity. And it turns out in trigonometry, when you have 2 times sine theta times cosine theta, that's the same thing as saying sine 2 times theta. So our final neat little equation right here will be range, or the horizontal distance, equals initial velocity squared sine 2 times theta over gravity. Now let's plug in our numbers so that we can calculate which angle will result in the max range. So let's say our initial velocity is 15 meters per second. Plugging that into our equation, we have range equals 15 squared sine 2 theta. We're not going to touch theta for now. Over gravity, which is 10 meters per second square. Of course, it's 9.8, but we're going to simplify things and make it 10. Now, a good rule of thumb is that if your exam allows you to use a calculator, you should go with 9.8. If it doesn't, then go with 10 meters per second square. So this means R will equal 225 times sine 2 theta over 10. So R equals 22.5 sine 2 times theta. Now let's go for each of our 3 angles, 30, 45, and 60. You can try 0 and 90 on your own and let us know what your answers are in the comment section down below. So the range for each of these angles will be 22.5 times sine 2 times the angle. So for that first one, 2 times 30, which is 60. For the second one, 22.5 times sine 90. And for the last one, 22.5 sine 120. So for the 30-degree angle, sine 60 is going to be 0.86. So we have an approximate range, so 22.5 times 0.86 is about 19.5 meters. For our 45-degree angle, sine 90 is 1, so our range is going to be 22.5 times 1, so 22.5 meters. And finally, for our 60-degree angle, sine 120 is equal to 0.86, so again, 0.86 times 22.5 is about 19.5 meters. So you can see how the angle of 45 degrees will maximize the range. And here's how you can understand this intuitively. Remember how I said that projectile motions are simply 2 motions in one? Well, think about it. You have a y component and an x component. What you want to do is find the sweet spot where you balance both. So if I were to throw this at a 90-degree angle up in the sky, you maximize that y component. If I were to throw it at a 0-degree angle, you maximize the x component. Well, 45 is that sweet spot where you balance both. And if you were to increase it a bit to 60 degrees, you're increasing your y component at the expense of the x component. And if you decrease it to 30 degrees, you're increasing the x component at the expense of the y component. 45 is the sweet spot. So here's a summary of the important equations that we derived during this video. And here are a few comprehension questions. Let me know what answers you get in the comment section down below. If you found this video helpful, be sure to like and subscribe to see all my content. And go crush that exam.